Assalamualaikum and hi to Sir. Today our group would like to present about device management, which is in chapter 7. So the presenter for today is me, NADHIRAH, IMAN, Aifaa and ELISYA. These are the group member question. Set 1 is going to present by NADHIRAH and IMAN. And set 2 is going to present by Aifaa and ELISYA. So, I am Nurul Najihah binti DZULKEFLI. I am going to present about the types of device, function of device management, and input-output request management. So, these are the types of device. The first one is dedicated device. It is assigned one process or one job at a time. The process only release device when it is completed. But however, it also have some drawback, which is it must be allocated for duration of jobs education, and it is inefficient if device is not used 100% of time. So the second one is shared device. Device is shared by several processes. For examples like using hub, peer-to-peer, and also direct access storage. Access will be interleaved between process, and conflict will be resolved using some predetermined policies. And the last types of device, it is a virtual device. Virtual device, it is a combination of dedicated and shared device. The combination of these two share to a mechanism. It is called a spooler. A spooler is controlled by a program, putting job in a queue and taking them on one at a time. So basically, a good spooler should let us change or cancel the order of the document. So these are the function of device management. The first function of device management is to monitor device status. Monitor the status of all device, including storage device, printers, and other. And the second function of device management is to enforce policies. Enforce preset policies on which process get which device for how long. The third one is device allocation. Deal with the allocation of device to processes. And lastly, the functions of device management is to device the allocation, which is deal with the allocation of device to processes, temporarily processes interrupted, and permanently when it is complete. So these are the input-output request management. I/O request is made by process involve transfer from memory to devices. Operating system via device manager handle this transfer via three models. The first one is I/O transfer controller. The second one is I/O device scheduler, and the last one is I/O device handler. So the explanation for the input-output traffic controller is actually it have three main tasks for each I/O request. So the first one, it will going to determine if there's at least one path to a device of the requested type available, and it will select appropriate available paths. Also, it will determine when the device is not busy or when the device it is available. And for the input-output scheduler, it is used to implement the policies to allocate device, control unit, and channel. So under heavy loads, when the number of requests is greater than the number of available paths, it decides which requests to satisfy first. And lastly, for the input-output device handler, it is used to perform actual data transfer. For examples like processes device interrupt, handles error condition, and provide details scheduling algorithm. Processes the I/O interrupt, handle error condition, and provide details scheduling algorithm. They are extremely device dependent. So each type of I/O device has its own device handler algorithm.
Assalamualaikum and hi, my name is IMAN binti HAMDAN. The topic I'll be covering today is I/O devices in the cloud, sequential access storage media, and direct access storage devices. So, in I/O devices in the cloud, when a user sends a command from laptop to access a high-speed hard drive located many miles away, the laptop's operating system continues to conduct many of the process that has been discussed in the chapter, and it will expect a suitable response from the operating system for the hard drive to work on. As a result, the concept discussed in the chapter will remain relevant even when the cloud expands its access to a wider range of devices. So the local operating system's role in accessing remote I/O devices are the same role performed accessing local devices. And then the cloud also provides access to many more devices. So you can access the data in many more devices using the cloud. Next is sequential access storage media. For example, we have magnetic tape. The magnetic tape will write and read the record in sequence from the beginning of a reel of the tape to the end. So, and the length of each sequential record is usually determined by the application of the program. And each record can be identified by its position on the tape, on the magnetic tape. So the data can only be accessed in the order it is stored, from start to finish, which means you can't jump directly to a specific location to access the data. It has to read everything in sequence. So the access time can vary widely. Sequential access on tape is generally faster than direct access method. This is because tape drives are optimized for linear data flow. The number of characters that can be recorded per inch is determined by the density of the tape. So the higher the density, the more number of characters can be recorded in the tape. So as you can see in the figure, it shows that 9-track magnetic tape with 3 characters recorded using odd parity. The tape will remain stopped until there's a request to access one or more records. It will not move until there's a request to access a record. So when there's a request to access, the reel of the tape starts to rotate and the tape passes under the read or write head. The magnetic tape moves under the read or write head only when there's a need to access a record. As I said before, it needs a request to access before it moves. If not, then it will stand still over there. The tape also needs time and space to stop, so there is a gap insert between each record. This gap is called inter-record gap, also known as IRG, which is about ½ inch long, regardless of the size of the records it separates. If 10 records are stored individually, for example, so there will be 9 half-inch IRGs between them. As you can see in this figure, we can assume that each record is only 1/10 inch, which means 5.5 inches of tape are required to store 1 inch of data, which is not a very efficient use of the storage medium. So in order to make it much more efficient, we can group the records into blocks before recording them on the tape. This technique is also known as blocking, and it occurs when the file is first created. So when you retrieve them, make sure to properly unblock them first. So the transfer rate can be calculated by multiplying the density of the tape with the tape drive speed, which called transport speed. So you can see there is a formula over here. And then on this figure, you can see there is 2 blocks of record, which is stored in the magnetic tape, which is each of them are divided by IBG. IBG is interblock gap. Interblock gap is a half-inch gap inset between each block, and it is more efficient than individual records and IRG inter-record gap. So each block can hold like 10 record, as I said before. And then the optimal block size is entire block fits in buffer. So the blocking has 2 distinct advantages. The first one is fewer I/O operations are needed, since a single read command can move an entire block of the physical record, which includes several logical record, into main memory. And then the next one is less storage space is wasted because the size of the physical record exceeds the size of the gap. And then there's also 2 disadvantages of blocking. The first one is overhead and software routines are needed for blocking, deblocking, and record keeping. Secondly, the buffer space may be wasted if you need only one logical record but must read entire block to get it. Lastly, direct access storage device, also known as DASDs. Direct access storage device includes all devices that can directly read or write to an arbitrary place in storage. The device can directly read or write to specific disk area. So the direct access storage device can be divided into 3 categories, which is magnetic disk, optical disk, and solid state flash memory. And the access time is not as wide as magnetic tape, and the location where you record the data can directly affect its access time too. So that's all for me. Thank you.
Assalamualaikum and hello everyone. My name is Aifaa Najihah binti WARDI, and I'm going to present to you about what is magnetic disk storage, the access times, fixed head magnetic drives and movable head magnetic drives. The third one is disk storage structure, and the last one is device handler strategies. Magnetic disk storage. So what is magnetic disk storage? It is a computer hard drives, and it is also a single platter or stack of magnetic platters. What does it mean by stack of magnetic platters? It is a magnetic material on each surface of a platter, which are on the surface and the lower surface. So this drive has 3 platters. Usually we'll have total of 6 surfaces of magnetic material. Next, magnetic disk storage have 2 recording surface, and each surface is formatted. It also has a read-write heads move in unison. So, the data is accessed using magnetic heads on an arm that move in unison, which is move simultaneously across tracks and sectors on the disk. Accessing a record. System needs 3 things. First one is cylinder number, second one is surface number, and the third one is sector number. Cylinder number is the vertical position of the track. Surface number is the physical surface where the track is located. The third one is sector number. It is the specific sector within the track where the data is stored. So, if this head is here, this head will be in the same position on another plater, and so on. We don't individually move the heads. We move them all at the same time. So, because the plater is rotating and the head is staying in the place usually, the head will be able to access this circle on the surface of the disc. Each head will be able to access the circle on its own surface, and all of these are going to be at the same distance from the spindle. This is called a track. All of the tracks at the same distance from the spindle form what is called a cylinder. The cylinder simply consists of one track from each surface, where the tracks are in the cylinders are those that can be accessed by different heads at the same time. Now, let's move on to access times. Access time in magnetic hard disk drives is the time it takes for the drive to locate and retrieve data. It is composed of several components, which are seek time, search time, and transfer time. Seek time is the time it takes for the read or write head to move to the desired track. This is the slowest component of access time and can vary significantly depending on the drive's design and usage patterns. While the search time is the time it takes for the rotational delay and the time to rotate the DASD. This is also known as latency and is typically half the rotation period of the disk. And lastly is the transfer time. It is the time it takes to transfer data from the disk to the main memory. This is the fastest component of access time and is influenced by the disk transfer rate and the amount of data being transferred. First, we go through at the fixed head magnetic drivers. The fixed head magnetic drivers refer to a type of magnetic disk storage device where the read or write head is fixed in position and does not move. To access a record on a magnetic disk, the system requires two pieces of information, which are track number and record number. For track number, this identifies the specific track where the record is located, while the record number, this specifies the exact position of the record within the track. The total access time consists of two components, search time and transfer time. For search time, it is the time that it takes for the read or write head to move to the desired track, while the transfer time, it is the time that required to transfer the data from the disk to main memory. Magnetic disk drives, DASDs, rotate continuously at a constant speed. The requested record can be in one of three basic positions relative to the read or write head. Immediately under the head, which means no search time is required, while the second one is on the same track but not under the head. It means a partial rotation is needed to bring the record under the head. And lastly is on a different track. It means a seek operation is required to move the head to the correct track. Magnetic disks generally have little access time variance, making them good candidates for storing low activity files and random access data. Blocking, which involves grouping related records together on the same track, can help minimize access time by reducing the need for seek operations. Now, we go to the movable head magnetic drivers. For the access time, it is the same with the fixed head magnetic drivers, but this one includes the seek time. For the fixed head, it only requires search time and transfer time, but for movable head magnetic drivers, it requires seek time, search time, and transfer time. For the search and transfer time calculation, it is the same as fixed head DASDs. For the blocking, it is a good way to minimize the access time. Now, we are going to go at the disk storage structure. The first one, this one is arm assembly. This is going to be the arm of the read and write head, and the back one is the read and write head. It is on the up layer and the lower layer. So, as the plater is spinning with the same speed, it will create track. So this is the track, this is the blue one, track, and the part of it is the sector, and as you can see, this is cylinder. It is created amongst the three platters of the track, among the three platters, and spindle is going to be at the center of the platter. Now, this is the top view of the hard drive. As the platter is spinning around, doing the rotational with the same speed, the read or write heads will create a track, which is A in the red color, and B is the sector, and C is the sector track, and D is the cluster. Now, we go at the device handler 6 strategies. Device handler 6 strategies are the rules used by the I/O device handler to decide the order in which multiple processes can access the device. The goal is to minimize the seek time, which is the time it takes for the read or write head to move to the track on the disk where the requested data is located. The types is, first one is first come first serve, second one is shortest seek time first, and the last one is scan, including look, and step scan, C-scan, and C-look. The first one is first come first serve. The requests are served in the order they arrive without considering the physical location of the data. The second one is shortest seek time first. The request closest to the recurrent head position is served next, reducing the average seek time. Third one is look. The head moves in one direction, servicing requests until there are no more requests in that direction, then reverse back. Fourth one is scan. The head moves in one direction, servicing requests until it reaches the end of the disk, then reverses direction. The fifth one is C-scan. Similar to scan, but after reaching the end of the disk, the head immediately returns to the beginning and starts servicing requests. This last one is C-look. It combines look and C-scan, where the head moves in one direction until there are no more requests, then jumps to the beginning of the disk. So the first one is first come and first serve. So as you can see right here, the queue starts with 98, 183, 37, 122, and so on. So the head starts at 53. So starting from the 53, it will go straight to the 98, and then it will go straight to the 180 until the finish of the queue, which is 67. So it will go based on the head path that comes first. Now the second one is the shortest seek time first. As you can see, this is the same queue as the first come and first serve, and the same head starts at 53. But the difference is, the shortest seek time first is going to continue the head path to the number that is nearer with the current head starts. So now the current head starts at 53, and it will go to 65 because 53 and 65 is just 12 track traversed. And then 65 is near with 67. And then between 37 and 98, 37 is nearer to the 67, and then it will travel back to the 37, and then 37 will go back to the 14, and it will go to the 98, and then and so on. So the third one is scan. The head will start at 53, but it will move until it reaches at the end of the disk. Until then, when it reaches the end of the disk, it will reverse its direction. And the fourth one is C-look. The C-look is the combination of looks and C-scan, where the head moves in one direction until there are no more requests, then jumps to the beginning of the disk. So as you can see, it starts with 53, 65, 67, 98, 122, 124, 183, and then it will move and jump to the beginning of the disk, and then until there are no more requests. That's all from me.
Assalamualaikum and good day to everyone. My name is ELISYA FATIMAH binti ABDUL HALIM. In this section, I will explain about optical disk storage, solid state storage, components of the input-output subsystem, communication among devices, and RIG. So optical disk storage consists of single spiring track, same size sector from center to disk rim, spin at constant linear velocity CLV, and more sectors and more disk data than magnetic disk. The important performance measure of optical disk storage are sustained data transfer rate, Its speed to read massive data amount from disk measured in megabytes per second (Mbps), crucial for applications requiring sequential access. Next, average access time. Average access time to move head to specific disk location, expressed in millisecond ms. Third feature, engage size hardware, which have a substantial impact on perceived performance. It buffers to transfer data blocks from disk, anticipating which data the user may want to retrieve next. Next, we see about CD and DVD technology. Firstly, CD. Data recorded as 0 and 1s. Bits refer to indentation and lengths refer to flat area. CD read with low power laser. Light strike length reflect to photodetector. Like striking a bit, scattered and absorbed. Photodetector convert light intensity into digital signal. Next, CDR. Compact disk recordable technology. It requires expensive disk controller, records data using write-once technique. Data cannot be erased or modified. Disk contains several layers, gold reflective layer and dye layer. Record with high power laser, permanent marked on dye layer. CD cannot be erased after data recorded. Data read on standard CD drive, which is low power beam. Lastly, CD rewritable disk and DVD rewritable disk. Data written, change and erase. Use phase change technology, which is amorphous and crystalline phase states. Record data, beam heats up the disk. State change from crystalline to amorphous. To erase data, the optical disk drive use a low energy beam to heat up that small area just enough to loosen the alloy and return it to its original crystalline state. Although DVDs use the same design and are the same size and shape as CDs, they can store much more data. It's red laser with a shorter wavelength than the CD's infrared laser. Make smaller pits and allow the spiral of the disc single track to be longer and wound tighter. Therefore, a dual-layer single-side DVD can hold the equivalent of 30 CDs. Next, Blu-ray disc technology. A Blu-ray disc is the same physical size as a DVD or CD, but the laser technology used to read and write data is quite different. The pits on a Blu-ray disc are much smaller, and the tracks are wound much tighter than they are on a DVD or CD. Blu-ray product can be made backward compatible so they can accommodate the older CDs and DVDs. And the Blu-ray's blue-violet laser has a shorter wavelength than the DVD's red laser. So, this allows data to be packed more tightly and stored in less spaces. Blu-ray discs are available in several formats: read-only, BD-ROM, recordable, BDR, and rewritable, BDRE. Next, solid-state storage. Solid-state storage is a type of computer storage media that stores data electronically and has no moving parts. Solid-state storage is made from silicon microchips. In solid-state storage, we will discuss about flash memory storage and solid-state drive. So firstly, flash memory storage. Flash memory is a type of electrically erasable, programmable, read-only memory (EEPROM) that's recognized in a grid of cells in row and columns. It's a non-volatile storage medium that can emulate random access memory, but unlike RAM, it stores data reliably even when power is disrupted. Flash memory is the technology used in removable media for numerous devices. It can be used to expand virtual memory space for some operating systems, and it was the precursor for solid-state drive. Flash memory is not indestructible. So the limitation of flash memory storage is the bits can be erased only by applying the flash. Next, each flash edge erasure causes the storage area to become less stable. Next, solid-state drive. SSD storage data permanently inside an integrated circuit, typically using flash memory. The flash memory inside an SSD means data is written, transferred, and erased electronically and silently. So how the solid-state drive compare to hard disk drive? So solid-state drive work electronically and have no moving part. The concept of seek time, search time, and rotational delay do not apply, suggesting that SSDs offer significantly better performance, require less power, and they are relatively lightweight and silent. So the disadvantage of SSD technology are catastrophic crashes, which mean when an SSD fails, it often does so without warning. That is, without the message or data error that can be forewarn a user of an impending HDD failure. Next, data transfer rates degrade over time. SSD and hard drive technology can be combined in one unit to create a hybrid drive. Alternatively, SSD and hard drive can be combined within a system, called a hybrid system. Both techniques seek to maximize the benefit of each device by storing data that change often or file of a smaller size on the SSD, while storing the huge files or those accessed infrequently on the hard drive. Next component of the input-output subsystem. Input-output channels are programmable units placed between the CPU and the control unit. Their job is to accommodate both the fast speed of the CPU and the slow speed of the input-output device, and they can make it possible to overlap input-output operations with processor operations so that the CPU and input-output can process concurrently. Channels use input-output channel programs which can range in size from one to many instructions. Each channel program specifies the action to be performed by the device and control the transmission of data between main memory and the control unit. Some systems also have a disk controller or disk drive interface, which is a special purpose device used to link the disk drive with the system bus. This drive interface controls the transfer of information between the disk drive and the rest of the computer system. The operating system normally deals with the controller, not the device. So at the start of an input-output command, the information passed from the CPU to the channel is as follows. Firstly, input-output command, read, write, close, and so on. Second, channel number. The third one, address of the physical record to be transferred from OR to secondary storage. And lastly, starting address of a memory buffer from which or into which the record is to be transferred. Because the channels are as fast as the CPU they work with, each channel can direct several control units by interleaving command, just as we had several machines directed by a single dispatcher. Next, we move to communication among devices. The device manager relies on several auxiliary features to keep running efficiently under the demanding condition of a busy computer system. And there are three requirements it must fulfill. Firstly, it needs to know which components are busy and which are free. Next, it must be able to accommodate the requests that come in during heavy input-output traffic. Lastly, it must accommodate the disparity of speed between the CPU and the input-output devices. Each unit in the input-output subsystem can finish its operation independently from the other. Meanwhile, at the other end of the system, the CPU is free to process data while input-output is being performed, which allow for concurrent processing and input-output. The success of the operation depends on the system's ability to know when a device has completed an operation. This is done with a hardware flag that must be tested by the CPU. It makes up 3 bits. The flag resides in the channel set status word CSW, which is in predefined location in main memory that contains information indicating the status of the channel. 3 bits represent one of the components of the input-output subsystem, one each for the channel, control unit, and device. Each bit is changed from 0 to 1 to indicate that the unit has changed from free to busy. Each component has access to the flag, which can be tested before proceeding with the next input-output operation to ensure that the entire path is free. So, next we see about direct memory access and buffer. So, direct memory access is an input-output technique that allows a control unit to directly access main memory. Once reading or writing has begun, the remainder of the data can be transferred to and from memory without CPU intervention. Mode of data transfer is used for high-speed devices such as fast secondary storage devices. Buffer are temporary storage area built into convenient locations throughout the system, including main memory, channels, and control unit. Used to store data read from an input device before it's needed by the processor, as well as to store data that will be written to an output device. So double buffer, while on record is being processed by the CPU, another can be read or written by the channel. So this is the figure about buffer. And lastly, RAID. RAID consists of a set of physical disk drive that is viewed as a single logical unit by the operating system. RAID begins with the assumption that several small capacity disk drives are preferable to a few large capacity disk drives because by distributing the data among several smaller disks, the system can simultaneously access the request data from the multiple drives, result in faster input-output performance and improved data recovery in the event of disk failure. So here how it works. Data is divided into segments called stripes, which are distributed across the disk in the array. A set of consecutive stripes across disk is called a stripe, and the whole process is called stripping. Figure 7.21, which is the next the short figure, show how the data stripes are distributed in an array of 4 disks. There are 7 primary levels of RAID, numbered from level 0 to level 6. It should be noted that the levels do not indicate a hierarchy but rather denote different types of configuration and error correction capability. So, however, these 7 levels do not tell the whole story. When 2 levels are combined, as discussed in nested RAID level later in this chapter, their strength can complement each other and provide substantial benefit. So remember, though, that adopting a RAID configuration often requires the purchase of additional disk drive to implement them, which immediately increase hardware costs. So that's all for me. Thank you.